Okay, so in this second lecture on reinforcement learning, we're going to be reintroducing value functions into policy gradient methods. First as a baseline to which we compare the returns that we sample, and then next to replace the returns that we sample using actor-critic methods. And then hopefully we'll get to covering a little bit of deep reinforcement learning, some of the issues with it that make it very complex, and some of the tricks that have been introduced to try and make them more stable. So let's start by introducing these baselines. So the baseline essentially works on recalling the invariance in the gradient that we had before to remove the past. So recall that the sum over the actions of the probability of each action multiplied by the gradient of the log of the probability of each action is just 0. And we can use this to basically just stick any function of the state in here, and it still sums over to 0. And using that, we can then insert some function of s into our gradient. So we do that, then we end up with the gradient of L theta is sum over trajectories with the probability of each trajectory, sum over the time steps within that trajectory, the reward, the return in the future of that transition, minus the baseline that we're at. This could be plus or minus, but we're just making it minus for what we're going to do next. And then we have the eligibility of the action. And our goal is, by introducing this baseline, is to essentially choose it to reduce the variance of this bracket. And thereby reducing the estimate of the gradient that we construct. So the obvious choice for doing that is the average of this other fixed term in the bracket, which is the return. And obviously it's going to be the average following on from that state. And that clearly is just the value function. So what we do is we reintroduce values. By ideally choosing B of S equals the value of that state. And I just think there was a mistake over here. So these should have time indices. This should be T. The only issue with this is that we don't have these exact values, and in general, they're very complicated to calculate. So our solution to this is to introduce a second function approximation for the value, like we did in the last course. And then we'll construct a loss function which we optimize in order to estimate these values. And we'll call this approximation V psi, with the weights psi. And the loss that we're going to choose for this for now is simply the error divided half, because when we do the derivative, we'll have the, okay, so this is going to be the sum over the states with the probability of being in each of those states under the current policy. So it's just the probability of at some point in some trajectory you're in this state when you run an infinitely large number of trajectories. And then we have the error between the value of each state, the true value, and our approximation for that state squared. So the factor of a half out the front, because when we do the derivative, you get the factor of 2 out of this. And obviously we don't know V pi, so this seems a bit contradictory, but it actually turns out that we can calculate this gradient quite efficiently. So in this case, we're then using, to optimize this, we use gradient descent, because we're trying to minimize the loss function, minimize the error. And when we calculate the gradient, what we end up with is the sum over states weighted by the probability of being in them. The difference between these exact values and the target, the estimates, and the gradient of value for that state. And again, this is still written in terms of the values that we don't have, but now we can substitute in the definition of these values. And what we end up with is then a sum over the states, a sum over future trajectories, where we're conditioning S0 to be S, and that we then have the probability of each of those future trajectories. And then we just have the return. So this is just substituting in the definition of the value from the last lecture into this equation. And then we can do exactly what we did with the policy, which is we just run a trajectory, sample the returns after each state. So for each state along that trajectory, the S0 is now that state, and then the capital T is the time until the end of the trajectory from that state in the trajectory. And then we can construct an estimate using one trajectory as before, which is given by the negative of the sum over the time steps, the difference between each return, and the value of the state that the return followed, and the gradient of the value in that state. And then if we use this V of psi as our baseline in the policy gradient, this bracket, this return minus the value, occurs exactly in the policy gradient as well. So we can just run a trajectory, calculate this bracket along each trajectory, and then use it to construct an estimate of both the value function and the policy at the same time, policy gradient, and update both weights simultaneously. Alternatively, we could alternate between updating the value for the current policy, then calculating the gradient with that value function. But that tends to be quite slow compared to just doing both at the same time. Now, obviously, since this baseline in principle averages out, it doesn't matter if it's inaccurate too much. But the more accurate it is, presumably the more it's going to speed up the learning process by giving us a lower variance gradient estimate for the policy. So we want it to be as accurate as possible. And the way this is usually imposed is by kind of saying that you choose the learning rate so that value function learns quicker than the policy, so that it's always very close to the true value function for the current policy. And so given that, what does this policy gradient do? So it, using this estimate of the gradient, L theta, L theta, it moves the weights to change the probabilities proportional to the future return, contrasted with what it expects the average future return to be in the current policy. What this is essentially doing now is whenever we run a trajectory and we calculate these differences, what we're basically saying is we sample a return in the future of an action, and if that return is higher than what we would expect the return to be on average, then we increase the probability of that action. If it's lower than the average, then we decrease the probability of that. And if they're all positive, then it will kind of gradually, the ones which are more positive will dominate eventually, and it will kind of increase the probability of the highest value action. So as I said before, the value should learn faster for it to be accurate. So in order to test this, we're going to go back to our excursion problem. And this time we're going to do it using tabular values as well as a tabular policy. And these tabular values, again, is basically saying we have one weight associated to each state. So we say v psi of x and t is simply psi of x and t, which is the weight associated to that state. And then the update is then that we do the derivative of this value with respect to the weights. We simply get that we get that each weight is the weight associated to each state is independent, so we simply have to we don't have to construct this big vector of updates for all of the weights. We can just associate each update to each weight. And to see that more clearly, just look at the code in the GitHub repository, and you'll see how it's kind of being that we're just storing a list of updates which we apply to the weight for each state that we visit along each trajectory. So then this gives you an update which is just for each state along the trajectory, we just say psi of x and t goes to what it was before plus beta, which is another learning rate for the value function, with the return minus what it was before. Okay, so when we apply this, what we find is that it performs relatively similar to how the last algorithm did. So what we have here, again, is the same plots as before. We have the samples on the left and the learning curve on the right. And what we can see is that, generally speaking, it actually learns slightly slower to start with in the first kind of 200, 300 episodes. But then after that, eventually it does achieve a higher average return. Part of that slowness is because in this kind of problem with the large learning rates that this has been set to, the policy very quickly becomes kind of almost deterministic. Not completely. There is some variance in those samples for the pink trajectories, but it becomes, because there isn't very high variance in the returns, by adding the baseline, what you can almost essentially be doing is just making that term smaller and therefore making the learning rate effectively smaller. So you could probably speed up the learning process with the value baseline by having the learning rate go up after a while and then come back down. So generally speaking, while this is good, it still has quite a high variance because the return, you're still using returns afterwards, and more complicated problems are very highly probabilistic policies and environments. The returns afterwards could still be quite high variance, and that could slow learning. So, as a solution to this, we're then going to introduce the values in another place, and this will bring us to the fairly well-known actor-critic techniques. The idea here is just that if we were to instead use multiple trajectories to calculate our estimate for the policy gradient, each action, a state action pair, would occur potentially multiple times. And after each of these state action pairs, you might have a variety of different returns that can occur under the current policy and environment. And when you combine all these together to construct your gradient estimate, you're basically just doing an average over those returns. And essentially all that's giving you is that average is then related to the value of the state that it goes to, or the value of taking the action it took in the state it took the action in. So then there's a question of, like, can we just replace the return samples with our estimate of the value? And by doing that, what we're essentially doing is replacing the future returns with our past experiences of their trajectories. This turns out to be actually exact, and you can do this quite easily. So the first step is just to rewrite our gradient estimate in terms of the probability of each state action pair occurring. So what we do is we take every time step where the same state action pair occurs across all possible trajectories, combine all of the probabilities leading up to that state action pair in each of those trajectories to give you a probability distribution for that state action pair occurring full stop across all trajectories. And when we do that, what we end up with is being able to write the gradient of the loss as the sum over state action pairs, this probability that I just described, the probability of that state action pair occurring, and then we have a sum over the future trajectories from that point, given that state and that action. where this is the return of each of those trajectories minus, it's still got the baseline in here, which we'll write as v pi for now rather than v psi. And then we have the eligibility. Okay. And then the next step is to just perform this sum over these futures, which only interact with this return. And by doing that, we can then replace this return with the value of the next state and the reward in between, weighted according to the probability of those transitions and rewards occurring. So we'd sum over the futures, which leads us to the sum over SA, S primed, and R of P theta SA, the probability of this occurring under the environment, and the difference between the value of the next state plus the reward minus the value of the previous state, which is just the baseline. And then again, we have the eligibility. And this term in the bracket here is something called the temporal difference. I'll just move that equation up from behind the camera in a second. Okay. And then this temporal difference is sometimes just labeled, the temporal difference error, sorry. And this is sometimes just labeled delta S primed Rx. And this essentially measures the error in what the critic, which is what we're now calling the value function, what the critic predicts the value for the current state is compared with what the value, compared with what it just experienced predicts that the value should be. So the reason we're now calling it critic is because it's essentially saying whether the action that the agent took, the actor, the policy, was a good action or a bad action. If the value that it says the next state is plus the reward in between is less than the value that it predicted, then it took a bad action. So that's all fine for the policy, but for the value function, we then need to reconsider our loss function. And the reason for this is that we could replace the future returns with the values in the same way that we did with the policy. But this is only an accurate replacement if the values are accurate. And this is fine for the policy because we can assume that the value function is learning quicker than the policy and it's always accurate relatively to the true values for the current policy. But for the value function, presumably, we have to start from somewhere where the value function isn't accurate. So in what sense does replacing the returns with the values give us an accurate estimate for the gradient? In reality, this is a good gradient to follow, a good estimate of the gradient, but there is a alternative perspective which can reassure us that this is the correct gradient to follow. So it's inaccurate estimate of the old loss function, or the gradient of the old loss function. So what we do instead is look at a new loss function based on the Bellman equation. And this is simply given by the mean squared difference between the right and left side of the Bellman equation that we looked at in the first lecture, relating the value of the state to the value of the next state. So this is given by LTD now to indicate temporal difference. The sum over states and actions, p theta A. Sorry, there's a slight mistake here. So this should just be the sum over S. And then inside the error, we'll have the sum over S primed, R, and A. The environment transition with the policy and the value plus the reward during transition minus, so this should be the psi now, because we're measuring the error in the Bellman equation for our estimates of the values. Okay. Now, the calculating the gradient of this object with respect to both sides of the Bellman equation would be very complicated, although it is a valid algorithm that people do study. But for simplicity, when we calculate the gradient, we're going to fix the target, as it's sometimes called, the this part here. So we're going to fix this target. So basically, it's going to say we're targeting what our current estimate for the next state was, and only varying the weights for the state that we're in. And then when we calculate this is called a semi-gradient method because we're ignoring the gradient of the target. And these turn out to be quite accurate in many situations, depending on the conditions that the algorithm is working in. We'll come back to that later. And then we just have a sum over the state, action, next state, and the reward. With the environment and the policy and the probability of being in that state to start with, and then we just have the difference between our prediction and the reward and our prediction for the next state and the reward and our previous for the current state. And that's multiplied by the gradient of the value. Okay, so this is the exact same estimate of the gradient that we would have got just by replacing the returns, but now what we're basically saying is that we're targeting the other side of the Bellman equation. And this seems a little bit more reasonable. It's debatable whether fixing the target is correct or not, but in many situations it does work fine. As long as the values aren't varying too quickly, then you're always you're trying to minimize the error with a moving target, and it produces good results. So one advantage of these actor-critic methods is that now that we are bootstrapping, now that we're replacing the future returns with our value estimates, we can now do online learning, which is to say that rather than waiting for the end of the trajectories, we can update after every single transition that occurs. So what that looks like is our gradient estimates then simply become, this is the temporal difference calculated using the approximate value function, so the v-psi, multiplying the eligibility for the policy. And then for the value function, we simply have the negative of this temporal difference error and the gradient of the value. So the results that we get when applying this to our excursion problem are very similar to what we had before, but actually slightly worse, surprisingly. Okay, so as we can see, to start with, the actor-critic algorithm in green actually performs slightly worse. For the first 200 episodes or so, it gets stuck quite low down, and then eventually it comes up and actually roughly matches the value baseline algorithm that we considered earlier in this lecture, which is given in magenta or pink. And then our original Monte Carlo algorithm is the one given in blue. And part of the reason for this is the structure of the problem that we're looking at. So because there's this layered structure in time and we only move one step, it takes a very long time for information about, for example, rewards related to the target propagate backwards along the state space, since the actor-critic is only aware of the estimate one step in the future. So if something occurs n steps in the future, it needs at least n trajectories before that then propagates backwards to an earlier value estimate. So this can slow it down in the short term, especially in problems like this with this particular kind of state space. The online learning in this case also doesn't get reused later in the episode because each state can only be visited once because the time progresses. But one advantage of this is that the value function that you can see over here is actually more varied as a higher entropy. And this can be an advantage if the environment changes, because it has a broader range of experiences. It's less locked into a particular deterministic set of actions. This can allow it to adapt more quickly to changes in the environment. So to provide an example that actually demonstrates that this algorithmic development we've done so far in this lecture is useful, we're going to consider a problem called cart pole. And this is if you want to experiment with this yourself, there's code we'll look at in a second, but this is implemented in the OpenAI gym, along with many other environments to test reinforcement learning in. And essentially what it consists of is a state space. So the cart pole that is named after is simply that you have a cart which has some hinge on it, and this hinge has a pole coming off of it. And the goal is to keep the angle of keep the pole upright, to keep it within some range of angles which are acceptable, and to achieve that for 200 time steps. And so the state is given by the position and velocity of the cart, and the angle and velocity of the end of the pole. So these are continuous degrees of freedom. So it's the velocity and position and the angle and everything can all take any value within some boundary, at least, for the position and the angle. The velocity is unbounded, it can take any value. And the actions are simply to apply a force left or right. And this force doesn't immediately change the direction necessarily, it just it applies an acceleration to the velocity, which changes how it's moving. So as I said, the goal is to keep the pole upright. And the way that we're going to do this, a lot of tutorials that you'll see online will try and do this using deep reinforcement learning of some kind, since there are continuous degrees of freedom. But you can solve this problem perfectly well just by discretizing the state space. So we'll take each of the degrees of freedom and bin it up into 10 bins. And if the state happens to be in one of those bins, then it has the same values and the same policy. So we discretize the state space. And then use our tabular methods that we've already covered. Okay, so we come over here. This is code which is available in the GitHub repository. And what we have here on the right are files containing the code for the tables and the learning algorithms. So these are based on, first we have this over here on the left. This is just the code creating all the objects and then running the learning algorithms, and it will also, when I run it in a second, it will run examples. So if I just do that now to demonstrate. What we should see is, one second. So we'll see a video pop up in the left corner. If you run this code yourself, setting up a Python environment containing the OpenAI Gym and MATLAB so that you have plotting software and NumPy, what you'll see is a video that will pop up showing the cart pole running. And this will it will fail to begin with because it's taking completely random actions. The pole will just fall over very quickly. And then it will run learning and it will spit out the learning curves for the 3 different algorithms. And then it will play a video of the actor-critic policy, which usually turns out to be the best one. So the code for this consists of first having this preprocessor up here, which is defined on the right. And this basically takes whatever the continuous state of the cart pole is and then turns it into a discrete index, which defines which component of the table to use to calculate the current value and choose the action. Then we have 3 policies and 2 value functions defined here on the left, which contain our policy and our value estimates. So these consist of this value class on the right, which simply returns the value using this forward function and updates the value according to an error that the algorithm has calculated using the step with a learning rate that you provide. And then we have this action, 2-action policy table here, and that allows us to sample actions at random according to the current policy using this action function, and similarly update the policy using step by providing it with an error from the algorithm and the eligibility. And then in this file, we have the 3 algorithms that we use, defined in a fairly unified way. So then if we run this video run, so you can't see that, and then when it finishes training in a second, so what you should be able to see at the bottom is that the average initial return is 23. This is when it takes random actions, so it on average survives about 23 time steps, but the goal is to survive as close to 200 as possible. And when this finishes training, so the blue curve is the running Monte Carlo for the cart poll. The pink curve is running the value baseline, which actually hasn't performed very well here, which is unusual. And then the green line is the actor-critic. And as you can see from these, if I return to the, well, as you can see from the graphs, the actor-critic performs much better. It struggles a bit to begin with, but eventually it, once the rewards start propagating around the state space, in later episodes, it gets to a very high average return very quickly. Whereas both the Monte Carlo methods seem to be struggling quite a bit. So we'll finish up just by looking at deep reinforcement learning briefly. So there are a few issues with deep reinforcement learning that don't come up so much if you're using a table or if you're using linear function approximation. And essentially, what it boils down to is that when you're using a neural network, reinforcement learning is very unstable with basic techniques. So there's a few reasons for this. The primary one is that in the algorithms we discussed before, especially the actor-critic, we made an implicit assumption that our samples of the states and actions that we were optimizing in were sampled independently and identically from the state action distribution. And while they likely are sampled from the state action distribution, they aren't sampled independently. And this is essentially because if you are running a long trajectory, the states and actions that you're in the future are very much highly correlated with states and actions that were earlier in the trajectory. And what this can do is lead to overfitting. Now, if you're doing tabular or linear methods, they aren't quite as susceptible to overfitting as neural networks, so it doesn't work too badly. But when you're using a neural network, they tend to overfit to the most recent things they've seen, even without correlations in the samples. So when you've got correlated samples, obviously the gradient estimates are correlated and it can overfit even more. So correlated samples cause overfitting. And what this overfitting essentially comes through as is a divergence in the weights. A second issue is something else we kind of ignored before, which is that because we're using these semi-gradient methods where we fix the target and then try and move our estimate towards this estimate of the target for the value function. What we essentially end up with is a moving target. And usually this isn't too bad. These semi-gradient methods are accurate as long as the data you're using is sampled on policy. But if your policy is changing rapidly, as it may be if your network is unstable, or if you're using online learning, in reality, you're probably not sampling the on-policy distribution perfectly because the policy is changing, and therefore the state distribution is changing along the trajectory. But your past actions were chosen using an old policy. And in those situations, or if you're using genuine off-policy sampling, which is how we'll solve the first issue, then a moving target, these semi-gradient methods turn out to be inaccurate. So we need to solve this somehow, which we'll come to in a second. And the final thing, which I've already mentioned, is that you have a changing state distribution, which means you're not necessarily genuinely sampling the state distribution under the current policy when you're doing online learning. The solutions we're going to cover to these problems are experience replay, and target network. So the way experience replay works is by reusing past experiences in order to both reduce the variance of the gradient estimate by having more samples, by having a larger batch of samples for each gradient estimate, and also to make the samples that you're using more independent from each other in particular. So this is clearly off policy because we're using past experiences that weren't necessarily generated by the current policy. And as I said, we construct estimate with past experience. And these past experiences that we store are the state, the action that was taken in the state, the following state, and the reward that we got going to that state, and the probability with which that action was chosen. So mu is the policy at the time that that experience occurred for taking the action A in the state X. And what this does is it clearly introduces a strong bias in our estimates of the loss function by not using data which is sampled from the current state distribution or using the current policy. It introduces a bias by incorrect sampling of SA, of state action pairs. Now, there are methods for trying to somewhat correct the sampling of the state, but they're quite complicated and don't necessarily provide a huge benefit. So we're going to ignore those for now and just focus on what we can do quite easily, which is to fix the sampling of the actions. And this is done using importance sampling. Where we essentially, if we were using actor-critic, for example, we would replace the temporal difference error. This should be the reward. We replace this with the temporal difference error multiplied by a ratio of the current probability of the action that temporal difference was sampled with occurring, divided by the probability with which that action was taken. And what this essentially does is, because we're sampling from the replay buffer, which is partly an expectation over mu, the policies that we use to generate those experiences, this ratio will then cancel out that factor of mu and reweight it, rescale it with a ratio of the current action. So if that action was very unlikely to occur in the current dynamics, it will have less of a contribution to the gradient. And this can help remove some of that bias, although not all of it. And what this replay buffer essentially does is, because we're using a collection of past experiences that were potentially from different trajectories or far in the past, they're uncorrelated with the current experiences that are occurring or just with each other. So it's obviously these samples in the replay buffer are slightly correlated, but not massively. So this reduces correlations in samples. So that's the that in principle solves the issue of the correlation in the samples that we use to construct our estimates. That's one issue solved, but it almost introduces a second issue, which is that we're now using very off-policy data, potentially. But we're using a moving target, which creates instability. We're using one of these semi-gradient methods. So there are a couple of ways of solving this. You can actually, as I mentioned earlier, use algorithms which calculate the gradient of the value loss function by taking into account the gradient of the target rather than ignoring it. But again, these are quite complicated. So we're going to go in the opposite direction, which is to actually fix the target for even longer. So we do this by fixing the network which we use to construct the value estimates for the targets for a period of updates rather than just a single update. And what this essentially does, especially combined with the replay buffer, is move the algorithm that we're running much closer to supervised learning. So now we have periods where our targets are fixed, our labels for the value function are fixed, and we're using large collections of data from a relatively constant collection of experiences, of samples. This moves us much closer to supervised learning. And this generally makes the algorithms much more stable as long as the period is long enough. And alternatively, you can actually just use an exponentially moving average, which is covered in the lecture notes. And the way this works is that we replace the temporal difference error given by v psi s primed plus r minus v psi s. We replace this with v psi primed of s prime plus r minus v psi s. And then every n updates of psi, we update psi primed to the current value of psi. And yeah, this fixes the target for longer, makes the problem closer to a supervised learning problem, and stabilizes the learning of the network. These two things combined can go a long way towards fixing the issues of using neural networks in reinforcement learning, but often a lot of other techniques are required to get them to learn quickly, and often very, very large amounts of data are required to learn. There's a couple other techniques mentioned in the lecture notes, but we'll leave that here for the lectures. And again, thank you for listening, and leave any questions in the comments or send me an email.